Welcome back, everyone. Let's finish up our discussion of carbohydrates, and with that, the material for our 4th hour exam, which is coming up as I speak in a week. Good, so we've covered some of the reactions that simple sugars, monosaccharides, undergo, ending up with, of course, forming these glycosides, which are full acetals made by treating any simple sugar you like with an alcohol, generally a small alcohol, and an acid catalyst. The mechanism is exactly the same as forming any other full acetal. So it's exactly what we talked about in chapter 19. There's nothing else to know. It's the exact same mechanism. There are also some important redox reactions of simple sugars, and I've picked one here. Incidentally, you're going to be insanely jealous of me. I literally drew that whole molecule in one mouse click. I can just pick hexoses. I've got a table of them over here, and I can pick the chair form. So I don't know what that is, but it's pretty cool. So just like any other aldehyde functional group, if you take one of these aldohexoses and you treat it with sodium borohydride, then it will reduce the aldehyde group to a primary alcohol. And of course, lithium aluminum hydride would do the exact same thing. In general, we like to use the smallest hammer that we can get away with. We don't immediately go for the sledgehammer when the little tack hammer will do just as well. In any case, these reduced compounds are called alditols or sugar alcohols. And I gave these words in the class notes. You might have heard of these. They show up as artificial sweeteners. Nowadays, you can actually go to the same aisle of the grocery stores you'll find sugar in and other artificial sweeteners, and you can buy like alditol or not that. You can buy xylitol. I know that one. So that comes from xylose. That's one of the 7 friends of D-glucose. So these things are very easy to make. Another nice thing about sugar alcohols that I've found out recently is that they've been used for decades in sugarless gum. And so they actually fulfill 2 roles, because not only are they, of course, sweet, but the bacteria in your mouth really, really do not like sugar alcohols. So you get 2 for the price of 1 there. There are also 2 different oxidation reactions that we can perform on simple sugars like this one. If you treat one of these aldoses, it doesn't even have to be an aldohexose like this is. It can be a sugar of any length, but as long as it is an aldehyde group. And if you treat a compound like that with aqueous bromine, remember, bromine is a good oxidizing agent. All of the elemental halogens are. The way you know that is because the oxidation number of Br2 or Cl2, the halogen out of his net, is of course 0, right? Because it's a pure element. But we know that halogens like to have an oxidation number of -1, right? Bromide, chloride, etc. So that means the halogen wants to get reduced from 0 to -1. That means it's going to go oxidize something else. In other words, it's an oxidizing agent. And so that's a way that you can remember that. In any case, I always found this really interesting, but aqueous bromine will oxidize an aldose like this to the corresponding aldonic acid, as it's called, I think. Yep, that's right there in your class notes. What that means is it oxidizes the aldehyde to a carboxylic acid and doesn't touch any of the other OH groups, which, again, I always found that fascinating, that something like aqueous bromine could be that selective, but it is. Nitric acid is an even more powerful oxidizing agent than bromine. And you can tell that because nitrogen's in the +5 oxidation state. That's the highest oxidation state possible for nitrogen. And it would very much like to have a lower oxidation number than that. So if you warm an aldose like this in nitric acid, you'll wind up oxidizing the aldehyde group and the CH2OH group, the primary alcohol group, both to carboxylic acids. And again, all of the other, any and all other OH groups remain untouched. and that type of compound is called an aldaric acid. Both aldonic and aldaric acids have some importance as biochemical intermediates, and they're also used to make other things as well. So with that, let's perform some wizardry and erase the board. Okay, presto changeo. Welcome back. That took you no time at all and took me a little while, but not too bad. Let's end off our discussion of the reactions of monosaccharides with an interesting comparison, because we have a way of converting a sugar, an aldose, to an aldose that's 1 carbon longer, and we also have a way to do the exact opposite, to convert an aldose to an aldose that is 1 carbon shorter. And those two methods are known as the Kilian Fischer synthesis and Wohl degradation, respectively. As always, I'm less concerned that you know the names than that you understand the reactions involved. And happily, all of these are both 3-step methods, essentially, that use only reactions that we've talked about already. We know the mechanisms, well, except for catalytic hydrogenation. I guess we don't really know that. But by and large, we've gone over these mechanisms and given them a full mechanistic analysis. So how would you convert a sugar to one that's 1 carbon longer? So let's say that over here we have some aldose, where R is just the rest of the sugar molecule. So all your OHs and Hs sticking off in all directions and CH2OH on the bottom. We learned in chapter 19 that aldehydes can be converted to the corresponding cyanohydrin. And that's all that this molecule is, cyanohydrin. You treat this with HCN, as we talked about in chapter 19, and you get the corresponding cyanohydrin. You will, of course, get both diastereomers at the anomeric carbon. That can't be helped. The second step is to reduce the nitrile with catalytic hydrogenation. So hydrogen and palladium, I expect platinum or nickel would also be fine. And you can see that we've effectively added H2 across the carbon-nitrogen triple bond, and you get an imine. And then in the third step, we simply hydrolyze the imine and go back to the aldehyde. And presto, we've gone to a molecule that's an aldehyde to a molecule that's an aldehyde, and there's a very sugary-looking carbon in the middle. That can be OH or H. You'll get both diastereomers again. And of course, diastereomers are quite easy to separate. You don't have to go through all that nonsense like you do when trying to separate enantiomers. Diastereomers have different properties, and so they're in principle quite easy to separate. Anyway, that mechanism we also covered in chapter 19 in the formation of imines, which is a reversible process. And incidentally, the formation of cyanohydrins is also reversible. You can drive the equilibrium one way or the other depending upon the nature of the reagents that you use and what's in the reaction mixture. But that's very clever, using 3 very simple reactions that we have already talked about and already know all there is to know about. We can convert a sugar to another sugar 1 carbon longer. The opposite process is called the Wohl degradation. So let's say that we have some sugar here, and here it doesn't matter whether we have just 1 diastereomer or both. That doesn't even matter. This carbon's gonna become our new aldehyde carbon. The first step is to treat the aldehyde with hydroxylamine. And this makes a special kind of imine known as an oxime, O-X-I-M-E. And that's in chapter 19. We talked about forming imines there. We went over the mechanism. It's the exact same thing we said before. The next step is to treat this oxime with acetic anhydride, which is a powerful dehydrating agent. And there are others, but I don't think you'd want to go with something worse than acetic anhydride. We covered the reactivity of acetic anhydride in chapter 21 and other acid anhydrides that are like it. They really like to react with water to result in 2 carboxylic acid molecules. So the result is you can see how we can remove the elements of water in order to make a nitrile. And that's exactly what happens. This now is a cyanohydrin. And so what we can do is drive the cyanohydrin formation in reverse by using a base such as methoxide ion. And I don't know that that's the only one that would work, but I know you don't want to use hydroxide, right? Because that would hydrolyze the nitrile and you'd get carboxylic acid. So I think you'd want methoxide or ethoxide. You might be given sodium methoxide. So again, be prepared for this to be given to you every which way. Owl will be owl, as we're all fond of saying by now. Anyway, this goes by the exact same mechanism of going from the aldehyde to the cyanohydrin, but in reverse. We just run it backwards. And you will wind up with an aldehyde molecule that's 1 carbon shorter than what we started with. And so the fate of the original aldehyde carbon is to wind up in a cyanide ion. So that, of course, is water soluble. That's going to go very carefully in the waste jug. And so that process is known as the wall degradation. Again, all of these are reactions we understand already. We're at the end of the term, and as I've said before, my ability to surprise you is limited at this point because we've basically seen it all. Good. Last of all, I want to make the point, we covered earlier, we covered in the previous video, how you can make glycosides in this manner by forming a fall acetal. We also saw how other hydroxyl groups in sugars can be alkylated and can react with other electrophiles. If you combine those two ideas, then you understand how to make a disaccharide. It's just like making a glycoside, only instead of using methanol, you'll use some other OH group on some other sugar molecule, a second sugar molecule. And those come together and lose a molecule of water, and you get a disaccharide. That repeats again as many times as need be, and you can get a polysaccharide, like starch, like glycogen, right? So, like cellulose. So certainly I don't expect you to memorize any particular structures of particular disaccharides, but my point being, if you understand how to make a simple methyl or ethyl glycoside, then you understand how to make a disaccharide as well. There's nothing else you have to know, except instead of like HOCH3 or HO ethyl, you have HO big sugar molecule. But other than that, it's the exact same idea, exact same mechanism, exact same everything. So one of the things, and really the last task I wanted to give you in this chapter is I think it's reasonable for you guys to be able to draw simple disaccharides, given enough cues. I know that I even went as far as saying sample exam question. So again, it's difficult not to, but please try not to get too overly married to the exact wording here. Right? The idea is just to give you enough information. And we already know, in principle, the structure of glucose. And from that, we understand, in principle, the structure of all kinds of other D-aldohexoses, like galactose and like many others. So here's one that I've given you, and I've also given you the answer. I thought it might be nice to come up with another problem here to end our video. So I'll leave that one up there. And while you wait for mere moments, I will go ahead and make another question like that. Okay, welcome back. Although, like I said, literally no time for you passed just then with the miracle of video editing software, which doesn't require all that much skill, but it's, I suppose, useful to know. Good, so let's come up with a different disaccharide. I'll again use glucose and galactose. I might not use galactose, but I would tell you how whatever sugar I gave you differs from glucose. Because like I said, if you know the structure of glucose, and even though it will be open book this time, I really do recommend you memorize the structure of glucose, especially if you're going on to biochemistry. That will be useful. You might there have to memorize all 8 D-aldohexoses. I would not be surprised. But for my money, if you memorize glucose, you in principle know, or D-glucose, you in principle know all the others. Good, so let's see. I, of course, am able to draw like whole chairs pretty easily. So I'm going to, actually, I could draw the entire galactose molecule if I really wanted to. Well, actually, the first one's going to be glucose, right? We're going to start with glucose. So that means that all of my non-hydrogens on my ring will be equatorial. And I'll leave the anomeric carbon for last once I figure out what's going on there. Oops. Good, so all of my hydrogens are going to be axial, or all my axial positions will be hydrogens. And so all of OH over here, OH over here. And I know that I'm leaving all of those alone because I'm given to start at carbon 1. I'm going to make an alpha glycosidic bond from carbon 1. So you start with the first number you're given, from carbon 1 to carbon 3 of galactose. That's what all that means. And so all of OH over here, I have a hydrogen over here, and over here I've got CH2OH. It's going to mess that up unless I say flush right. Nope, flush left. There we go, or better. Well, the hydrogens are colliding. But in any case, so now over here, we're at carbon 1. This is the glycosidic carbon. I think I'll tell that to do that, so it stays out of the way a little bit better. Good. So this is, I'm given that it should be an alpha glycosidic bond. So since the vowels don't go together, alpha is down. So that means my oxygen is going to be over here. And that's going to be the oxygen that connects to the galactose. So I also know this should be a hydrogen, since one's going to be the oxygen, the other is going to be the hydrogen. This over here is an alpha glycosidic bond, meaning it's pointing down. There we go. And I'm only labeling it so you can see. Of course, if it doesn't specifically say to label it, then you don't have to. But I'm just doing that for the educational possibilities there. Good, so now this is going to connect to what? We're given that we need to connect it to carbon 3 of galactose. So what does galactose look like? Well, galactose looks just like glucose, except it's different at carbon 4. So the OH at that carbon will be axial. This is carbon 4 over here. So I'll have to remember to make the OH axial there. Otherwise, only the hydrogens are axial. Now you'll notice another thing here. This problem does not say what to do at the hemiacetal carbon. In this one, it says at the hemiacetal carbon, which is unambiguous. There's only one hemiacetal in the whole molecule. It says to draw the alpha anomer. This doesn't say what to do. So what do you conclude? Hopefully, what you're concluding is, doesn't matter. You pick. It can be alpha or beta. But before I get to that, I want to figure out where all of my H's and OH's and so forth go. I just want to figure out, I'll leave carbon 1 undecided as of yet. So again, my H's are going to be axial in carbon 2, axial in carbon 3, and also axial on carbon 5. My OH's will be equatorial on carbon 3, also equatorial in carbon 2, but on carbon 4, that'll be axial. And so I'll have a hydrogen over here. And of course, I've got CH2OH over here also. Let's say flush left so that it doesn't mess that up. Good, and then I would make the hemiacetal either beta or alpha if I was instructed. Here I've not been instructed, so I'm going to choose to make it beta. I just flipped a coin and the coin came up beta. Good, so that's the molecule that I need to connect to this oxygen of the glucose. How do I know where to connect it? Well, at carbon 3 of galactose, carbon 1, carbon 2, carbon 3. That means instead of OH, this O is going to be over here. And so that's exactly where I'm going to connect it. Let's see if I can do this. I think I might have not made my job particularly easy. Let's try this. We'll just make a really long bond. There you go. So that's at carbon 3. I'll put the 3 in so you have a visual aid. That's at carbon 3 of galactose. And unless I've gone completely insane, which heaven knows is always possible, unless I've gone completely insane, that answer would receive full credit if this were an exam question. Likewise, if this OH and H were switched in this particular case, full credit, since it doesn't say what to do with the hemiacetal carbon. So you choose, alpha or beta. And I think that's a good place for us to end. And with that, that's going to end our material for exam number 4. Not the final exam, but the 4th hour exam. I'm thinking of actually producing our chapter 31 video, which is on polymers, fairly soon, most likely before we have our 4th exam. But again, that chapter 31 material will not be on exam number 4. That will be fair game for the final exam. And then, if I have the time, the inclination, and the energy, like I said, I'll also try to produce a video on chapter 29, which ordinarily would have been part of the material that's fair game for the final exam, but not this time. But I'll produce it if I can, as I said, just in case anyone's interested. So other than that, we'll stop there for now. Please stay safe and well.